Okay, we acknowledge we're hosted on the lands of Mississauga of Anishinaabe and the Haudenosaunee Confederacy and the Wendat. We also recognize the enduring presence of all First Nations, Métis, and Inuit people. Today is August the 1st. Wow. Okay, day 2. So today we're going to talk about inverse functions and simplifying polynomials. Okay, polynomials are basically functions, right, with more than one term, more than 2 terms, more than 3 terms, right? You guys know that from grade, I believe grade 10, a monomial is 1 term, binomial is 2 terms, and trinomial is 3 terms. So we just say anything more than 1 is a polynomial, okay? Simplifying polynomials and inverse functions. That's what we're going to be talking about today. And then you have the worksheets for today, and then you'll have a quiz that's due by the end of the day today. Okay. There's still a few people that have not done the quiz from yesterday. So I'm not sure who's in the chat or who's in the Zoom. So let me just check something. Let me know in the chat if you did not do the quiz yet from yesterday. Just let me know in the chat. I'm just going to take a number. So, okay, so 1 person. Anyone else? You couldn't find where it was. Anyone else? Okay. Okay. So it's right here. Okay. You click on that, it takes you to the quiz. Right. That's why it's a hyperlink. Right. Or you can go to quizzes. Right. That's why it says quizzes. Right. You can do it. You shouldn't do it while I'm talking. You can do it after I'm done. Okay. Right. So my point is, I'm asking you guys to do this. Yeah, after class is okay. But again, you have to meet the deadlines, right? So when I hear, I don't want to pick on anyone, but when someone says I couldn't find it, I didn't get an email, right? So I'm telling you guys to be serious, right? There is absolutely no wiggle room for missing due dates, okay? If you come back to me, like I'm asking you guys, and there's a bunch of people who are not in this Zoom, but you cannot miss deadlines. You just cannot, right? I have to give you 0 if it's not done by a certain time. I'm giving you guys a grace this week, right? So grace this week. So if you didn't do it yet, do it. But it's not acceptable. It's not acceptable to say, I forgot. It's not acceptable to say, I couldn't find it. It's not acceptable to say, I was too busy for work, and that's why I couldn't do it. It's not acceptable. All those are not acceptable reasons to miss deadlines and to not do it. Because in the end, it's you sign up for this course, and this course says you need to be doing the stuff every single day. Okay? So you have to take that serious. So if someone emails me and says something, sir, I don't want to use the word, but an excuse that's not acceptable, like I forgot, that's one of those excuses. So you forgot. So then therefore, it's like saying I forgot to get paid. That my boss forgot to pay me, and that's the reason they tell me. That's the reason why I didn't get paid. It's not an excuse. You have a deadline to follow, so follow it. Okay. So please do it after class. So that being said, we're going to do inverse function and polynomials, simplifying polynomials. So we're going to go into content. And let me look at it from a student point of view. That way, you're not getting a whole bunch of stuff. let's see for the quiz. Can I see the next quiz? Yeah, there's a quiz for today. And then with his worksheets for today, August 1st worksheets. All right, so August 1st worksheets right here. And then the content. Unit 1, and then we're going to go to August 1st. Yeah, August 1st right here. So worksheet. So it's 2 worksheets for August 1st. Okay. So let's get into the lesson, inverse function. So you can see this is the actual lesson right here. And we're going to go through the video, and then I'll play the video, and then I'll stop it at certain spots and then emphasize some of the things, some of the concepts. So here we go.
Last lesson for the transformation.
Can you guys hear it? I just want to make sure you guys can hear the video. Okay, good. Okay.
Unit, it's the last kind of type of transformation. So we've looked at horizontal stretching, compressing, vertical stretching, compressing, shifting left, right, up, down. We've also looked at something called a vertical and horizontal reflection. The inverse of a function is actually kind of like a diagonal reflection. It's going to be reflecting a function, and the notation, we're going to be reflecting across the line y equals x. So inverse of a function, we have a notation to indicate that we're finding or have the inverse of a function. And the notation is this f with this thing that looks like an exponent of negative 1.
Okay, so let's try to get the beginning. What are you saying there? So if this is my, shoot, something. If this is my graph, no. Okay, so that's my graph, and I'm going to draw a parabola. Use a different color, so I'll go like this. This is a parabola. Okay, so the parabola is equal to y is equal to x squared, right? Or we can write it like f of x is equal to x squared, right? It's the same thing, right? We replace y with f of x. So the inverse of this is basically replacing, so the actual inverse is sort of like what he was saying in the beginning. You're basically reflecting it about this line here, this line I just drew. That line is considered y is equal to x. It's like a diagonal line, okay? So when you're doing inverse of anything, you basically are mirroring it over this line called y is equal to x. So what would that look like? If I'm going to draw this parabola in inverse, it would be like this. All right, now it looks like it's mirrored. And basically what that now parabola would look like now, or what's it called, is basically saying, so let me back up a little bit before I even get to that. So when we say inverse, we start off as wherever this x is and the y, they basically switch locations. So now I'm going to have it like this. X is going to equal to y squared. Okay, that's what that is. That's what that means. Okay, and then what it also means is now I'm going to do the inverse of that. So the inverse of that is I have to get y by itself. All this stuff it's going to come up later on, but I'm just showing you right now. So you can see it first and then absorb it when you see it again. So now I bring the square root over to the other side, it becomes square root x. Okay. Okay. And technically, it's supposed to be, let me do this properly. It's supposed to be y is equal to plus or minus. Okay. So does that mean you have plus or minus values here? And then we replace y with f of x. So now, and since we're saying this is inverse, right, it's going to be inverse equal to that plus or minus. I should say plus or minus there, so we can see that properly. Okay. So it's equal to plus or minus the square root of x. Right. Now, if I have plus or minus, that means x has to be positive in the square root. But when it comes out, it can be plus or minus, which will basically tell me that my value of my y, which is dependent on my x, is going to be, my y value is going to be plus or minus or plus. Okay, so that you can see how I get two values of my y because I have plus or minus here. So x comes out positive, and then it's going to be plus or minus, and then y is in terms of the plus or minus. Okay, so that's a little bit quick summary of how you go from the regular function to the inverse function. Okay, so we're going to go through examples, and it's going to be talking along the lines of this. Okay, so let's go.
One, but it's actually just notation. It's not an exponent. To get the inverse of a function, to reflect it diagonally across y equals x, all we have to do is essentially switch the x and y coordinates with each other. So if f at 5 equals 13, for the inverse of the function, so that's what this little notation here, that -1, that tells us we have the inverse. For the inverse, f at 13 would be equal to 5. So here we have the point 5, 13. That's what that tells us. For f at x, when x is 5, y is 13. But for the inverse of f at x, when x is 13, y is 5. So all that's happened is the x and y coordinates have just swapped with each other. So the inverse of a function has all the same points as the original, except the x's and y's have been switched with each other or reversed. If we're actually going to draw the inverse of a function, all we need to do is have the points of the original function and then swap the x's and y's with each other, and then we can plot those, and we have the graph of the inverse of the function. And it's going to look like it's just been reflected diagonally across the line y equals.
So that's what I was saying, reflected diagonally across the y, the line is y equal to x, okay? It keeps saying that, so this is the line right here, okay?
X. So let's actually do a question where we find the inverse of the function g at x. So g at x is equal to this transformed version of, it looks like our parent function is root x. So I'm going to, since this square root here, that tells us that our parent function, I'm going to call the parent function f at x. The parent function is root x, so we'll have to remember what that looks like. We'll have to apply the transformations to that parent function using our a, k, and c values to get the points for our transformed function g at x. And then we don't want to graph g at x, or we do want to graph g at x, but our end goal is not only to graph g at x, we also want to graph this, the inverse of g at x. And remember, this exponent, or it's not an exponent, it's a notation. This -1 is not an exponent. It's just a notation telling us it's the inverse of g at x, which means we just take all our x and y coordinates from g at x, and we switch them all with each other, and we will get the coordinates for the inverse of g at x. And I think on this page over here, I forgot to scroll down, but I actually made a note here. And important to note, inverse of f at x, this -1 here, it's read as the inverse of f at x, not f to the exponent of -1.
Okay, did you get that? Like I wrote over here, it's that f of x with a -1, it just means it's the inverse, okay? We have to just remember that. It's not to the power of -1, okay? It's not to the power of -1. It just means it's just inverse. That's all it means. That's what you're saying there.
This -1 does not behave like an exponent.
Because if you were to think of it as an exponent, that means you're saying this is the same as this. No, it's not. It's not the same. Okay, this is not the same. This does not work out. Okay, it just means the inverse. Like I did over here, the regular one was f of x equal to x squared. The inverse looks like this. Okay, so just remember that.
This does not mean 1 over f of x. It doesn't act like an exponent. It just means the inverse of f of x. Let's get back to this example. So first, key points to the parent function root x. Hopefully you remember, I chose perfect square x values so that we can get integer values for y. Square root each of those, 0, 1, 2, 3. That's what the parent function root x would look like. Well, what would the transformed function g at x look like? Okay, well, let's start with the horizontal transformations. K is negative a half. So first of all, that's going to be a horizontal reflection because it's negative. So the x's are going to have to be multiplied by a negative value to change the sign of them. And the k value, we always have to flip it. So we have to do 1 over a half, which gives us 2. So it's going to be a horizontal stretch by a factor of 2. So we'd have to multiply the x's by 2. Combine those two things.
Okay, I'm going to fast forward a little bit of this because I feel like some of this stuff, we haven't talked about transformation yet. Okay, so because I think we're going to talk about transformation afterwards. So this stuff here, if you remember in grade 10, you did transformations for parabolas, right? And when parabolas was in vertex form, let me just jog your memory about that. You know what? Let me not do that. It's a little bit confusing. But right now, we're just graphing the inverse, okay? So in this case here, this would have to be manipulated to the inverse of it, and we haven't done that yet, okay? So let me see if he gets into rearranging this into inverse. Let's see. Does he do that? Probably not. Okay. No, he doesn't do that. So one of the things you can do, right? So what we're doing here basically is getting the inverse of this, right? But here is the original function, right? And basically these are the transformation areas for this, okay? And what he's doing here is getting the transformation of this function and then getting the inverse of this function. And all you're doing was once you get the transformation of this, so let's just say we fill this up, okay? Let's fill up this table. So now once you have this table here, and this is key, right? Because once you get this table, everything becomes easier. But this table is the part where you have to figure out. So what we're saying here is, when you look at these, I guess I want to say, what's the word I'm looking for? Translations, I should say. So these are the translations and transformations. So A applies to your Y, and then K applies to your X, and then C applies to your Y. Okay. The only thing is you probably don't remember, because we haven't taught it, that when you apply a half to X, that means you're actually doing, it's shrinking by 1 over K. 1 over K, and if K is a half, means 1 over K is going to equal to 2. And this fact's going to be negative 2. So that's why you have multiply all the X components by negative 2. So the original was 0, 1, 4, 9. I'm going to multiply each of them by negative 2. So I have anything times 0, 0. 1 times negative 2 is negative 2. 4 times negative 2 is negative 8. 2 times negative 9 is negative 18. And on for the Y, the translation and transformation is based on the 2 that's here, which is a negative 2, and then the 3 that's here. So I'm going to multiply all my Y's by negative 2, and I'm going to add 3. So 2 times 0 is 0, plus 3 is 3, and so on. Now what you do for the inverse, like what we just learned, all we're doing is just swapping x and y. So whatever the value of x now becomes y, whatever the value of y becomes x. So that's the case. I'm going to have 0 for y and then 3 for x. You're going to swap these. Okay. Now I guess we can go into the plot. I had to go through it because I think it wouldn't make any sense to skip it all. You'll see some more of it later on, but I had to go through it.
Notice I made my scale go by 2s so that I could actually fit these points onto the graph. So the point 0, 3.
So basically he's going to graph the transformation function. So it looks like that. Back up.
Here. So remember the parent function root x, just roughly, it looks, well, not quite like that, more like this. That's what root x looks like, like curved looking. It only exists to the right, of the line, x equals 0, right? Because we can't square root a negative number. But keep in mind our transform function, it's been horizontally and vertically reflected. So instead of continuing up to the right, it's going to be flipped vertically and horizontally. So it's only going to be continuing, oops, and I should do this in blue, down to the left. I didn't connect those very well, but you can imagine me going through those points with a smooth curve. I'll try and do it a bit better.
So all he's doing, he's redrawing the parent function as a translation. But then what's happening is we have the translation. Now we're getting the inverse of that translation. Okay. So this is the g of x, and now he's going to show you the inverse of the g of x. That's the g of x, the translation.
Continuing in the downward to the left direction. So that's what our function g at x looks like. If we want the function inverse g at x, what we have to do is we have to take all of these points and just swap the x's and the y's with each other. So instead of 0, 3, we'll use the point 3, 0. So 3, 0, negative 18. So I just kept all these same points, just swapped the x's and the y's with each other. So if I plot those points, 3, 0, 1, negative 2, so 1, negative 2, negative 8, negative 18. I believe that's negative 18, 10, 12, 14, 16, yeah. I would get this function.
Now, if you look at that function that he just drew, right, because it's an inverse, right, the inverse is always rotated about the line as y is equal to x, right? So if I were to draw that y is equal to x, this is the line that's y is equal to x. I'm not drawing it exactly, but basically it's mirrored from here to here, okay? You can see it's mirrored from here to here. So that is the inverse. So this will become, this is the inverse of this function right here, okay?
And notice this is our transform function. This is the inverse of our transform function g at x. So the inverse of g at x looks like this. And hopefully you notice this looks like it was a diagonal reflection through the line y equals x. So if I drew the line y equals x, it would look like this. And notice the inverse of g at x, oops, let me fix that. The inverse of g at x is just a reflection across this line. Each point has just been reflected.
Basically, each point on the original g of x just got flipped, right? So whatever was x, whatever x and y components you had, it was flipped over on this side over here. Okay, so that's basically the inverse.
Next thing I want to do is I want to look at, okay, we can make the graph of the inverse, but what if I wanted to write the equation of this?
So now this is the part which gets a little bit tricky, is writing the equation, because you have to, like, depending on the equation, you may have to do certain things. So here is the steps to do it, right? So like I said, you replace x with y, and then wherever you have, then you switch the x and y variables, and then you isolate for y. And once you isolate for y, you turn y into inverse y like this, inverse f of x. Okay, so we're gonna have to go through an example to kind of understand that. Here's an example right here, right? G of x. So let's just play it out.
For y. So here's what it looks like. So replace g at x with y. So y equals 3 at x over 4. Inverse functions, the x's and the y coordinates switch with each other, so we'll do that in the equation. Instead of writing y, we'll write x. Instead of writing x, we'll write y. And now we just rearrange this equation algebraically to isolate y. So multiply the 4 over, and then divide the 3. And then lastly, we'll write the proper notation. Instead of writing y, we will write the inverse of g at x. Right? We no longer have g at x, we have now the inverse of g at x. It's equal to 4x over 3. So that one's done. This one, function is h at x. Let's write the equation algebraically of the inverse of h at x. So we start, replace h at x with y. Swap the x and the y with each other, so x equals 4y plus 3. And now rearrange the equation to isolate the y. So move the 3 over, so x minus 3 equals 4y, and then divide the 4. And then now that it's rearranged to isolate y, we replace y with the notation for the inverse of h at x. So inverse of h at x equals x minus 3 all over 4.
Okay, so basically you're going to go through more examples. So we'll play a couple more examples. I think, yeah, let's play one more example, and then I think we're done. I'm going to play the next video.
I don't know if we need to I don't think we need to do that example. That's similar to what we already did. But C, so f at x, let's write the equation for inverse of f at x. First by changing it to y. Then by swapping the x and y with each other, so x equals y squared minus 1. So now we want to isolate y, so x plus 1 equals y squared. And then to move the squared over, we have to square root, but then don't forget we have to consider both possible answers for the square root of x plus 1, the positive and the negative, or else we would only get half of the graph for the inverse of the function. And now that y is isolated, we can go ahead and replace that with the symbol for inverse of f at x equals plus or minus the square root x plus 1. Let's do last example for this one. When we have a quadratic written in standard form, to be able to write the equation of the inverse, first thing you're going to have to do is convert it to vertex form. Well, first change f at x to y. So y equals 2x squared plus 16x plus 29. Notice that there's two x's in the equation and one of them is squared, so we can't collect. So what we're going to have to do is we're going to transfer this to vertex form by completing the square. So hopefully you remember how to complete the square.
Completing the square you guys would have did in grade 10 when you guys had to transform standard form to vertex form, right? This is a parabola. You're transforming the standard form, which that's what it is, into a vertex form. Okay, that's what he's doing right now. So let's fast forward a little bit. He's doing completing the square. So that means you put a bracket in the first two first two terms, and then you, in this case, he factors out the 2 from the 2 terms, okay? And then as he factors out the 2, now he's gonna look inside here. It's like you're gonna add a, I'll play it here from here, because he's gonna tell you what you do. It's like adding a fake 0.
Squared to get us a perfect square trinomial in the brackets. So half of it is 4, squared is 16. So add and subtract 16. And then we take the negative 16 out of the brackets so that all we're left with is a perfect square trinomial in the brackets. Take it out by multiplying it by the 2 that's out front, which gives us negative 32 plus 29. Inside the brackets, we have a quadratic. It's a perfect square trinomial. If we find the numbers that multiply to 16, add to 8, it's 4 and 4, so we could factor it out.
Over here, this is how you do it, right? This here is like adding a fake 0. If I add 16 minus 16, it's adding like just basically, it's a 0, right? So, but then you need to do this when you're doing completing the square, because now you can basically factor, complete the square, factor, you take out the 16, negative 16 to get out, and then inside the bracket, you can factor that, okay? The thing is, so how you got 32 is because it's in the bracket. If I take that negative 16 out of the bracket, there's a 2 that's in front of the bracket. So I have to multiply the negative 16 by 2 in order to take it out of the bracket. So now it becomes negative 32, okay?
X plus 4 times x plus 4, which is x plus 4 squared. Negative 32 plus 29 is negative 3. Here's our quadratic. It's now in...
Okay, so now that is in standard form, right? So now you're gonna have to convert this into inverse, okay? So how do you do that? He's gonna go through that right here, right? You replace whatever, wherever x was, you replace it with y. So now y is inside the bracket, you can see, right? Now what you have to do is isolate, get y by itself. After you switch it now, y is in the crowd. Now I have to isolate the y, okay? So you bring the 2 over, divide by 2, and then, or first of all, you bring the minus 3 over, it becomes a plus 3, so x plus 3. And then everything else underneath, you divide by 2. Okay. And then, okay, well, I have a square root. Okay, and I'll play from here so you can see.
2. And now I'm going to have to move the squared over. And remember from before, we're going to have to consider the plus and the minus, both options when we square root this, so that we get the entire function and not just half of it. And then lastly, you'll move that plus 4 to the other side. Becomes a minus 4. I'm going to put it in front. So negative 4 plus or minus the square root of x plus 3 over 2 is equal to y. Y is now by itself, so I can write the inverse notation, inverse of f at x.
Okay, so that's the inverse of that function. Okay, so now let's go over to the next one. Well, we still got some time. Simplifying polynomials. So here you have, by the way, you have questions on this. Okay, let's look at this. Let's look at some of these questions first of all, to get you to practice. See what it looks like. Inverse of a function, right? So sketching, you can do the sketching. You can simplify, basically inverse these equations. Okay, and then the answers over here. Okay, so let's go on to the next lesson. Sorry about that. So the next lesson is sharing my screen. So inverse of a function, simplifying. There we go. So simplifying, yeah, I just realized there's a bunch of these. So let me look at, so simplifying polynomials, which you're gonna have to know. There's a bunch of videos here. I don't have time to go through all these videos, but you need to go through them on your own. So adding, subtracting polynomials, we can do that. Multiplying polynomials using the FOIL method. We should know the FOIL method from grade 10. Okay. There's a part 1, part 2. So let's look at the part 2.
Number 6. Okay. This time we have two binomials being multiplied by each other, and then we also have another factor out front that's being multiplied by these as well. Okay. Remember, when you're doing multiplication, the order of multiplication does not matter. Okay. What I'm going to do is multiply the.
Okay, so this is not really a big deal, because I think you guys should know this. Basically, this is just multiplying, this is just doing the FOIL method, right? So remember the FOIL method? So the FOIL method, if I have a bracket like this, my bad, it would be, let me change the color, it's not working. So first times outer times inner times last. So if I do all that and I get an answer and I still have this -2 on the outside of the brackets, I'm going to have still -2. And I have here, I multiply all this out. So I'm going to have here -4 times 4x times 7x. Was that 28x? And then -4 times -6, or 4 times -6, that becomes -24x, right? This is squared, by the way. And then inner here is going to be -35x. And then here's going to be plus 30. Okay. So that's, so then you just simplify that, and then basically 2 multiplies what's inside there. Okay. So 2 bracket, and then I have 28,8 x squared, and I have, looks like I have here 59 x, and then plus 30. Right? If I have the 2 multiply each one, then I'm going to have a bigger number. Okay, for each coefficient. Okay, so so this is how you do this type of simplifying. Let me just close that.
The binomials first, but I can't forget that there's a -2 out front. Okay, so I'm just.
Yeah, so I wanted to just touch base on another one. Okay, so that was multiplying polynomials, common factoring. You guys should look at that. Factoring simple trinomials, factoring complex trinomials. So let's look at the factoring complex trinomials. Trinomials just means it has 3 terms. Okay, remember that.
Okay, so here's a lesson for section 5.5, factoring quadratics in standard form. So factoring quadratics in the form ax squared plus bx plus c. In this lesson, our a value is always not going to be 1, and it can't be factored out. In the previous lesson that we did for section.
Yeah, so here's an example.
Don't skip that ad. In the next 30 seconds, I'm going to show you how to start a business on Shopify. Go to shopify.com and sign up for your free trial.
Okay.
Numbers you multiply to give 12, and also these two numbers need to add to get.
So this is easy, right? In the sense that when you're doing factoring, this one here, using product and sum. Remember that, product and sum, right? So 2 numbers that multiply to give you 12, and then two numbers that add up together to give you 7. So this is just review for grade 10. So this is not like a full lesson we need to go through, but it's just review, because you'll get polynomials where you have to just use all the skills that you've learned from grade 10 and then some new ones now. So here, what two numbers? Well, I'm thinking that would be 4 and 3. So 4 and 3 together, multiply to 12, and 4 and 3 added together gives you 7, right? And then when you write it out, you're gonna have this. Y is equal to x plus 3 bracket x plus 4, right? That's fine. But when you have a question like this, it gets a little tricky, because I can't factor out that 2, or maybe I could, and this one I probably could, because 2 can go into 2, 2 can go also into 12. So I could, there you go, see, I'm taking out the 2. And then here, can I factor this? And yes, I can. I can factor. I can use product and sum factor, where two numbers that add up to -1, and then two numbers when they're multiplied together give you -6. Well, those two numbers are going to be -3 and +2, right? He's going to write it up there. -3 and +2 gives you this, okay? So y is going to be equal to this, okay? Okay, so you may have questions that are trickier. And here's a question that's trickier, this one over here. 3x plus, what's 3x squared, actually, not bad. 3x squared plus 8x plus 4. Now, you cannot divide the 3 out. So you're gonna have to do still product and sum. But the way it works is gonna be the product of 3 times 4, which is 12, right? And then the sum of +8. So you need to find two numbers that add up to 12. Okay. And when you sort of multiply, it gives you 12, right? And when you add them together, it gives you 8. What two numbers do that? I want to see in the chat. I want to get you guys involved now. What two numbers multiply together to give you 12, and when you add them together, give you 8? What two numbers are they? I want to see if you guys are listening. Only one person is listening. Yeah, okay, you're right. Right, 2 and 6. Right, so two numbers, right? So 2 times 6 gives you 12, and then 2 plus 6 gives you 8. Okay, so that would be the factors you can use, and then you're gonna have to rewrite that. So let's just go here. You're just using a table, which we can just figure that out, but you use a table, right? We know it's 2 and 6. And then you have to write out the equation, right? So when you write out the equation, right, you have to, over here, go back to here where my mouse is. You rewrite it, and then you write 3x squared plus 2x plus 6x plus 4. Then you factor by grouping, right? And he's going to talk about that right here, right? So I can factor by grouping. Let's go back to here. I can factor by grouping this, right? So let's go ahead, factor by grouping, so you can see that for the first time. So you have your 3x squared. Now this here turns into 2x plus 6x, and then you have plus 4 over here. So now when you do factor by grouping, I'm going to put brackets around these columns here. Okay. Okay, so I factor that. I basically, what can I do from in this bracket? I can take out x. So over here, I can take out x. So let me just actually just do this whole thing for you guys. You can see it. I take out x on this one here, and I'm left within the bracket 3x plus 2. And on the other bracket, I can take out I can take out 2 from both of these, right? So if I take out 2, I'm going to have here 3x plus 2. Just ignore that sound, please. Just go, hold on for a sec, guys. Okay, you're gonna hear some noise in the background, just to disregard that. Okay, so now when you are, now this is factored by grouping. Now I can basically take the x and the plus 2 and put it in as one factor, x plus 2. And then the other factor is 3x plus 2. Okay, that's going to be annoying. So just hold on for a sec. Okay, we're going to pause until that noise goes away. Okay, hold on. Okay, so the noise is over. So that's basically, this is factored. This is another way to factor, right? He's going to go through the motions and you're going to see the final answer is the same thing.
Sick of all the ads like this one? Just head to adskiller.com, click on Activate Now, add ads.
Okay,
3x plus 2. Okay, so this is a 3x plus 2. This term has a 3x plus 2. Since both of those have that in common, we can factor out that binomial because both terms have common factoring. Go back.
so you can see we got the same answer, right? So you need to know how to do this type of factoring, okay? So I'm not going to hold up anymore because we're getting close to that time, 10 o'clock. I'm going to show you one other factoring. All these are basically things you need to know in order to, I guess, to be able to simplify polynomials, okay? So we talked about, that was complex trinomial factoring. The simple one is just doing product and sum. We talked about that. And a perfect square. Let's look at that, a perfect square. Okay.
Welcome back, grade 10 math. We're going to continue with chapter 5 today. Chapter 5 is about quadratic expressions. We're going to do section 5.2. It's special products. Okay, in section 5.1 we learned how to multiply binomials. In this section we're going to learn about some special cases when we're multiplying binomials. Okay, so first off we're going to learn about perfect square trinomials. Okay, before we learn the rule for that, let's just work on expanding these two.
Okay, let's get into a perfect square first of all, because we already know how to do that. That's grade 10 stuff. Fast forward into perfect square. Okay, so Okay, so let's just look at an example of a perfect square. Okay, so here's the rule of a perfect square. Okay, so you can see here, if I have x plus 3 and it's squared, right? You can, instead of doing this whole multiplying, the whole, instead of doing, let me just write it on here, right? Because if you have x plus 2, right, x plus 3 like this, that's the same thing as saying x plus 3. I can finish writing this on my screen, times x plus 3. It's the same thing, but you don't have, but instead of doing, and then doing the FOIL method, you know, that times that, and then that times that, instead of doing all that, right, you can just fast track it because you already know it's a perfect square. So the way to get the quickest answer is just using this rule here. So I know I'm going to have an x squared because I just already know, based on that, I know I'll have x squared. Okay, so I'm saying here x plus 3 squared is going to equal to that. I'm going to have x squared for sure. Then I know that my middle terms are going to double, right? So if I have 3, it's going to be plus 6x. I know it's going to be doubled. And then my last term, it's multiply itself again. So I'm going to have 9. And you can see here, so it's always it's like a fast way to basically, perfect square is a fast way to actually get to the answer. Okay. So now I'm going to let you go. Not let you go just yet. So I'm going to show you the worksheet. So let's just get out of this.
2 rules for perfect square trinomials. If you are ever asked,
Okay, so let's get out of this. And let's look at the worksheet questions. Here it is here. Let's go to it. Let's see what you guys see. Again, it's not for marks. And these are the questions we're going to do, right? Multiplying polynomials, common factoring, factoring this, special products. Okay, so these are questions that you're going to do. Okay, and that should help you for the quiz. And again, it's not for marks, so you don't have to do every single thing and you don't have to hand it in. But this is, you know, a good way to practice. Okay, and then again, it's practice not just for now, it's just for the test too. So that is what you're working on today. And then you have the quiz that's due today. And those people who didn't do the quiz yesterday, please work on it. Okay, that is it for today. Okay, I'm gonna let you guys go, let you guys start your day. It's 10 o'clock. Past 10, you guys can go ahead and start doing the work you need to get done. Okay, so have a good day and take care. Bye.